Hypothesis test errors can be a really tricky topic. So I'm going to take a few minutes here to talk a little bit about power and beta. So we got beta and we got power. We're going to talk about it in terms of significance level as well. So we're going to focus in on this top distribution here. Now, just to review, a hypothesis test is when you have a parameter, like you have some idea of what a parameter could be, and then you're trying to prove that maybe it's something different. Maybe it's less than, greater than, or maybe that just doesn't equal your assumed parameter. So we're going to start here with a null hypothesis, and we make a sampling distribution out of it, right? Now, so underneath here, I usually like to do this. I encourage people to do this, at least when they first start doing hypothesis testing. Draw these little p hats or x bars. The reason is, a lot of times we tend to forget what we're doing here. What we're doing here is we're looking at a bunch of possible statistics. So basically, you have a parameter within a population. Now, you're not going to get that parameter every time you do a sample. What happens is you get variation when you take samples because it's not always going to look like, it's not always going to look like your population. If you do a random sample, it's going to hopefully do a pretty good job of getting something that looks like it. But that doesn't necessarily mean your statistic is always going to be your parameter. You might get a statistic. Hey, maybe if you're lucky, you get the statistic that's right on with your parameter. Maybe, however, you get one that's way out there. Not exactly what you expect from your parameter. Maybe a lot less, a lot more. That can happen. So that's what you want to remember. We're dealing with the sampling distribution, a collection of statistics based on a parameter. So we're going to do a hypothesis test based on this sampling distribution. We assume that Ho here is our parameter, our null hypothesis. This is what is true about our population. These are all the statistics we'd expect to get based on that. However, say we go into this hypothesis test assuming this is our parameter, when in actuality, our parameter is something way down here. We have a whole other distribution here of what the parameter really is. And this is what all the statistics really should be when we get this. Now, it can be a bit dangerous because you can get statistics based on that false parameter that you would expect within your alternate here, which in this case we're going to say this is our actual parameter. We don't know this typically, but we're going to try and prove it. So we have a hypothesis test. Maybe, we have our null, which for the sake of what we're doing, we're going to say our null is false. It's not true. We don't necessarily know that going in, but for the sake of what we're doing, we're going to say it's not true. We're going to say our alternate is actually true here. So, you're doing your hypothesis test. You set a significance level. And that significance level means this is all the statistics you choose as your rejection zone. If you get any statistics to the right of this line that you're going to say, okay, if I get one of those, then that's going to cause me to reject my null hypothesis. It's going to tell me my null isn't true, and I'm going to reject it. So let me expand this a little bit. Perfect. So up here is my rejection zone. That's my significance level. If I get any of these when I do my hypothesis test, I'm going to say, all right, if I get this, I'm going to reject that null that I've established here. So here's the thing. You can move this significance level. Maybe you decide, hey, I'm going to make a bigger rejection zone. If I get these statistics, I'll reject my null hypothesis. Maybe you want to make it smaller. And let me tack this on too. Maybe you want to make it smaller. Sometimes you do that. Sometimes you have a smaller significance level. You say, I'm really only going to take these statistics to reject my null hypothesis. There's some danger doing that, however. As you can see down here, in our case, we have the actual distribution because we're going under the assumption that, hey, this is what it actually is. This is the distribution we're dealing with within our population. And these are all the statistics from that. So what happens here is down here, this right here to the right represents your power. Right to the right represents beta. Now, what is that? Now, what beta represents is the probability of not rejecting your null when you should. So down here, these are all the statistics within this actual parameter, within this sampling distribution, that'll cause you to reject your null hypothesis when you really shouldn't. So that can be a bit dangerous. So sometimes what happens is you move that significance level. By doing that, watch what happens. When we make that significance level higher, we decrease the probability of making a type 2 error. A lot of times we like that. You might be like, oh, okay, that's good. If my alternate is true here, then, I have a much better chance of rejecting the null hypothesis when I should. That is power. Power is the probability of rejecting the null when you should. And over here is beta, which is probability of failing to reject when you should. Now, there are a lot of activities that explain this really well. I like this little animation. I was showing my students this, and they said, hey, that shows me pretty well here. So the significance level, watch what happens with my significance level. When I make that significance level smaller, I create the probability of making a type 2 error. Why? Because I'm making that rejection zone a lot smaller. And by doing that, that means there are less statistics that I could get that would cause me to reject my null hypothesis. If I want to reject my null hypothesis, that's a bad thing. Because you'll notice here, right here, these are statistics I want to get to reject my null hypothesis. Getting a lot less. When I increase my significance level, watch what happens. I have a lot more statistics in that rejection zone, which means my power gets increased. I have all these statistics that would cause me to reject my null hypothesis when I should. You also know that beta gets smaller, because now I have less statistics that would cause me to fail to reject that null when I should. So this is a great visual of the relationship of, let's see, I'm going to get rid of these highlights here. Oops, didn't want to do that. So when I take that significance level and I make it smaller, it increases the probability of making a type 2 error. It also decreases my power. When I make my power greater, I increase that significance level and I decrease the probability of making that type 2 error. What can be tough as statisticians is sometimes trying to find that balance, because a lot of times we really don't know if our null is true or our alternate is true. So that's where that balance comes in. And that's why a lot of times we use 5% as our significance level. It seems to be a pretty good balance, because it gives you a fair number of statistics based on your null hypothesis that'll cause you to reject it. It gives you just enough. And also, based on, what the alternate could be, a lot of times it gives you a decent power and doesn't really give you a very high beta level, which is the probability of making a type 2 error. So again, just to have that visual again, increase the significance level, beta gets smaller, power gets bigger. Decrease your significance level, beta gets bigger, power gets smaller. Hopefully this helps you a little bit with type 1 and type 2 errors, and again, beta, power, and significance levels.